Any substance that has mass and occupies space is called matter. It is made up of small particles called atoms that cannot be further divided. This idea was first proposed by the Greek philosopher Democritus back in 460 BC. However, due to the lack of scientific evidence, Democritus's ideas were considered mere speculations and ignored for 2000 years until John Dalton proposed the atomic theory of matter in 1808. Dalton proposed that atom is the ultimate particle of matter. This theory is called Dalton's atomic theory. It postulates that all matter is composed of atoms that cannot be made or destroyed. All atoms of the same element are identical. Different elements have different types of atoms. Chemical reactions occur when atoms are rearranged. Compounds are formed from atoms of the constituent elements. Dalton's atomic theory was able to explain the laws of conservation of mass, multiple proportion, and constant composition. However, it could not explain the results of many experiments conducted by the scientists in the later part of the 19th century and 20th century. For example, it could not explain the electric nature of matter as explained by Michael Faraday through his experiment in 1830. Michael Faraday found that when electricity is passed through an electrolyte, which is a solution that conducts electricity, chemical reactions resulting in the deposition of matter at the electrodes take place. This experiment proved that electricity consists of charged particles, which in turn indicated the electric nature of matter. The structure of an atom, however, was demystified only when William Crookes conducted experiments to study electrical discharge through gases in 1879. The apparatus used for his experiments consisted of a glass discharge tube, now called cathode ray tubes or Crookes tubes, and a high voltage source of 10,000 volts. The discharge tube was sealed at both the ends and was fitted with a thin piece of metal called electrodes at each end. It had a side tube fitted with a stopcock that connected with a vacuum pump to control the pressure of the gas or air contained inside the tube. Crookes observed that at a low pressure of 0.01 atmospheres, when high voltage of 10,000 volts is applied across the electrodes of the discharge tube, current starts flowing inside the tube. To further study the behavior of this current, he punctured the anode inside the cathode ray tube and coated the glass tube behind the anode with a fluorescent material, such as zinc sulfide, and then repeated the experiment. This time, he noticed a bright spot on the coating behind the anode, which confirmed two things. One, the current consisted of invisible ray of particles, some of which could pass through the perforated anode. Two, these rays were emitted out of cathode and moved towards the anode. These rays were named cathode rays. Some other facts about the cathode rays were discovered in 1897 by J.J. Thomson and other scientists through a series of experiments. In one of his experiments, Thomson observed that if a pinwheel is placed in the path of the cathode rays, the ray caused the pinwheel to rotate. This implied that cathode rays are made of material particles that produced a mechanical effect. He then observed that if a metal foil is placed in the path of cathode rays, it becomes hot. This implied that cathode ray produced a heating effect. Thomson also observed that if a solid object is placed in the path of cathode rays, it produced a sharp shadow of the object. Therefore, he concluded that cathode rays travel in a straight line. However, when he applied an electric field to the setup, the cathode rays deflected towards the positive plate of the electric field. He observed the same result on applying a magnetic field. Therefore, he concluded that the cathode rays consisted of negatively charged particles, which he named electrons. Through his experiments, Thomson also concluded that the properties of cathode rays do not depend upon the material of electrodes and the nature of the gas present in the cathode ray tube. This led him to the conclusion that electrons are the basic constituents of all atoms. Thomson then tried to calculate the charge-to-mass ratio of electrons by applying electrical and magnetic field perpendicular to each other, as well as to the path of electrons flowing in a cathode ray tube. He observed that the amount of deviation of the electrons from their path depends on three main factors. 1. The magnitude of the negative charge on the particle. The more the negative charge, the greater the deflection. 2. The mass of the particle. The lighter the particle, the greater the deflection. 3. The strength of the electrical or magnetic field. The stronger the field, the higher the deflection. When only electric field is applied, the electrons deviate from their path and hit the cathode ray tube at point A. Similarly, when only magnetic field is applied, electrons strike the cathode ray tube at point C. By controlling the deviation of electrons by varying the strength of electric and magnetic fields and accurately measuring on the amount of resultant deflections, he calculated the charge-to-mass ratio of an electron, which equals 1.758820 into 10 raised to the power 11 coulombs per kg. The charge and mass of the electron, however, remained unknown until another scientist, Robert Millikan, devised a method to calculate them in 1909. In order to calculate the charge of an electron, Millikan conducted the famous oil drop experiment by using the apparatus shown here. It consisted of a transparent electrical condenser with one metal plate at the top and the bottom of the chamber. Plates connected to a battery such that the upper plate is positively charged and the lower plate is negatively charged. An atomizer to spray oil into the condenser through a hole in the upper metal plate. A telescope to view the movement of oil droplets. And a source of X-ray to ionize the air inside the electrical condenser. Using the atomizer, Millikan sprayed oil droplets into the electrical condenser. As the droplets fell through the upper plate hole, he measured the rate of fall and used it to calculate their mass. He then ionized the air inside the condenser by passing a beam of X-rays through it. The X-rays displaced electrons from air molecules, which negatively charged the oil droplets. On applying voltage to the upper positive plate, the charged oil droplets got attracted towards it against all gravitational and electrostatic forces. Millikan then varied the voltage to strike a balance between the acting forces and to make the oil drop stationary. He then calculated the change on the droplet from the mass of an oil droplet and the charge on the plate. He found that the magnitude of electrical charge, Q, on the droplets is always an integral multiple of the electrical charge E. That is, Q is equal to NE. Knowing the values of Q and N, Millikan calculated the charge on an electron to be 1.6 into 10 raised to the power minus 19 coulombs. The mass of the electron, or ME, was then determined by combining the results of Millikan oil drop experiment and Thomson's value of E by M ratio, and was found to be 9.1094 into 10 raised to the power minus 31 kgs. Just like the discovery of cathode rays led to the discovery of the negative particles called electrons, the discovery of anode rays led to the discovery of the positive particles called protons. Anode rays, also called canal rays, were discovered by E. Goldstein in 1886, when he repeated the cathode ray experiment conducted by Crookes with a perforated cathode instead of a perforated anode. He observed that discharge tubes containing a perforated cathode also emit a glow at the cathode end. Goldstein concluded that in addition to the already known cathode rays, there is another ray that travels in the opposite direction. Since these rays passed through the holes or channels in the cathode, he called them canal rays. They consisted of positive ions, whose charge and mass values depended on the gas inside the discharge tube. Hydrogen gas produced the smallest and the lightest positive ions, with a magnitude of charge same as that of an electron, but with a positive charge, that is, plus 1.6 into 10 raised to the power minus 19 coulombs, and a mass that was found to be similar to that of a hydrogen atom, that is 1.67 into 10 raised to the power minus 24 grams. The mass of the positive particles originating from the other gases in the discharge tube was found to be whole number multiples of the mass of those originating from hydrogen gas. Therefore, the positive particles from hydrogen gas carrying one positive charge and mass equivalent to a hydrogen atom were taken as the fundamental particles of any atom and were named as protons. By 1913, after performing a considerable amount of research on the charge and mass of negative and positive subatomic particles, scientists tried calculating the atomic mass. It was determined that the atomic number of an element is equal to the number of protons present in its nucleus. It was thought that since each proton has one unit mass on the atomic scale, the mass of an atom must be the number of protons present in the nucleus, as electrons have negligible mass. However, it was discovered that the mass of all protons in an atom put together is much less than the actual mass of an atom. It was thus concluded that the excess mass was due to some other particles present in an atom that had considerable mass but no charge. Later in 1932, James Chadwick proved the presence of these heavy, neutral particles through a series of scattering experiments. In one of his experiments, on bombarding a beryllium plate with alpha particles, Chadwick observed the emission of a neutral particle whose mass was equivalent to that of a proton. He named this particle as neutron. After all the subatomic particles were discovered, it was concluded that an atom is made up of protons or positively charged particles, electrons or negatively charged particles, and neutrons that are neutral particles. The table here summarizes the properties of these fundamental particles.